Okay, so you're moving which one?
So instead of Tuesday morning, the Monday one is staying the same.
Okay.
My Tuesday one is not going to be.
And you're going to go with Matt
I'm going to do Thursday.
Thursday?
Yeah, from 1:30 to 3. Yeah, so I'm just in that block.
And Allison is back over here.
Yeah.
She has been. I never switched it. Okay, first announcement. First announcement is Tuesday morning. Erica's Tuesday morning office hour is going to be now along with Matt Thursday afternoons. I guess lots of you are going then, so now there'll be two of them to help you. So that'll be better. So, and then as we said before, Allison is no longer Wednesdays afternoons; she's Monday afternoons. Okay. So this one has changed to this. This one has changed to this. Okay? And maybe if I have a spare moment, I'll actually fix this, okay? But it's on the video. Let's try to remember that. Second announcement is next semester, 271. By a minor miracle. I am going to teach it. It was a minor miracle because I'm teaching this class again, and that would normally not happen, that I would be able to teach both 270 and 271 in the same semester. 270 was the priority, but it's happening, so I'm going to teach both. So this is 271. It's a 17116. It meets 9 a.m. Monday, Wednesday, Friday. So come if you've enjoyed this semester, if you're learning something, let's keep it going, okay? That's an announcements. That'll stay there. So if you ever forget, I'll leave that announcement up. Okay, any other questions before we start? Please. Okay. What's going on with recitation times?
They're just kind of only Monday, Wednesday, Friday, from 10:30 to noon.
Okay. Yeah, I doubt that they'll be able to switch that. So hopefully you can make something work. I don't think so. It's right after class. Is that Monday, Wednesday, Friday, right after class? Yeah. So I can inquire, but it's unlikely they would switch it. Other questions? Okay, so let's pick up where we left off on Friday. That's okay, because we're not using the internet right now. Okay, ready to start. Here we go. So we're developing these rules or shortcuts for finding, given a accumulation function, we're developing these rules or shortcuts to quickly find a rate of change functions in closed form. That's what we're doing. So on Friday, these were the four that we ended up with. What is the rate of change? So see if you remember what these are. So given x to the n, how would you find the closed form version of the rate of change function? Given a constant function, given a constant times of functions, or given the sum of functions. In each of these cases, what rule did we derive to be the rate of change function represented in closed form? Could you write those down? Do you remember? What about x to the n? N times x to the n minus 1. What about a constant function? Rate of change? 0. What about a constant times a function? The constant times the rate of change. The constant times the rate of change. And the sum of functions is? So it's going to be the sum of the rate of change functions, which is the best case scenario, right? It's just like you go one function at a time, and you do each of those rate of change functions individually and then add them, just like they're added to start with. Okay, so that first one we call the power rule. Next one we call a constant function. Next one we call the constant multiple rule. And then the last one, the sum or difference rule. Sum or difference. So if it was minus, if f of x minus g of x, the rate of change would be the rate of change of f minus the rate of change of g. Okay? So here is a function z, and we're going to apply all the rules above to find the exact rate of change function. We're going to do this one step at a time. So as finding these rate of change functions gets more and more complicated and there's more things that we're working with, the first thing we'll always do is we'll look at this and we'll say, what is the overall structure of that function? What is the overall structure of it? Is it what? Is it a constant multiple structure? Is it a product of two functions? Is it a quotient of function? Is it a sum and difference of functions? Okay, so this one, what is its overall structure? What is its overall structure? When you look at that whole thing in the big picture, z has what structure? Yeah. Sum and difference, right? Sum and difference. This is the sum and difference of four different terms. So we're going to apply that. That's the rule we're going to apply first. Okay? So we're going to apply the sum and difference rule. And so basically, the rate of change of z with respect to x is going to be what? The rate of change of each of these individually. And then added or subtracted, whatever applies. So it's going to be the rate of change of 9x to the 8th with respect to x minus the rate of change of x to the 5th with respect to x plus the rate of change of 1/4 x to the minus 2 with respect to x. That's a 2. And minus the rate of change of pi squared with respect to x. Okay, so now we've got four rate of change functions to do. And we come to this first one, the rate of change of 9x to the 8th. And the first question we ask is, what is its structure? What is its structure? 9x to the 8th has what overall structure? 1, 2, 3, or 4? It's not 1. It's 3. It's 9 times a function. You see? The overall structure of that is the constant multiple rule. It's 9 times another function. So what's that? So that would say that this is equal to? How would we rewrite this using the constant multiple rule? 9 times the rate of change of x to the 8th. Did you see what happened? So the structure of that was not power rule, it was constant multiple rule. And the constant multiple rule says that the rate of change is going to be the constant times the rate of change of the function. Okay, what about this? That's power rule. So now we're ready to use it. Okay, so we do minus the rate of change of x to the 5th, which is? Yep, so our power is 5, so that becomes the coefficient. And then our new power is 1 less. Okay, what about this? 1, 2, 3, or 4? 3 again. We're going to have plus 1/4 the rate of change of x to the minus 2 with respect to x. Okay, what about this? 1, 2, 3, or 4? It's power rule, right? No, it's not. This is pi squared. What is pi squared? That's not x to a power. That's a constant. Pi squared is a constant. Rate of change? 0. Okay, now we're ready to do the final solution here. I'll just erase and rewrite. So 9 times the rate of change of x to the 8th is 8x to the 7th. According to the rule, it'd be 8x to the 7th. So I'll just erase it. It's 8x to the 7th. And then we got this one left to do here. Okay, what's the rate of change of x to the minus 2? Negative 2 becomes the exponent. or the coefficient, sorry, negative 2 x to the, okay, it's not 1 closer to 0. It's always 1 less. Always 1 less. So your negative exponents get further from 0, right? So it's always 1 less. Negative 2 minus 1 is negative 3. Okay, so we got it. So we can simplify. We get 72 x to the 7th minus 5x to the 4th minus 1/2 x to the minus 3. Any questions on using the rules here to get the rate of change of z with respect to x? Anybody have a question? Do you follow? Yes, sir.
How are you able to tell what number 1 and everything? I had mistook that as power 4 on the
Because it's 9 times a function of x. Power rule is just x to something, right? There's no, see when you look at the power rule up there, there's no coefficient in front of the x. It's x to something. Well, this is 9 times x to something. That means you're using the constant multiple rule first.
All right.
Okay. But so now this will be something that very soon you can do. In one step, you can go from here to here. But I just want you to see how the individual rules are playing out. Identify the structure and use. So pretty soon your brain will just be doing these rules simultaneously, and that's great. But at first, we really want to see them playing out one step at a time. Other questions? Okay. So what do we learn when we find a closed form expression of a rate of change function? That was what we just did. We just did that. We had an accumulation function, and we found a closed form expression of the rate of change function. Okay? So here's what we had. Given that z of x was this, the rate of change function for z can be expressed in closed form like this. That's what we just found, right? We just used our rate of change rules to find the rate of change function expressed in closed form. And what's closed form? Closed form means rapid outputs, rapid values of the dependent variable for given x values, right? If x is 1, we get the rate of change just like that. If x is 10, we get the rate of change just like that. That's what closed form means. Okay? But we also learned something else. We also learned something else when we found the rate of change of z with respect to x. So I'm going to let you talk for a minute and see if you can articulate what we also, another very important result we found when we did that exercise. See, take a minute and see if you can articulate it to the person next to you. Go. What else did we learn? Okay, I'm guessing the success rate was a little bit low there. Okay, that's my guess. So I'm going to start you. We also learned that every accumulation function expressed in open form as what, then what. Okay, so now I'm getting you started. Do it again. See if you can do better now. Okay, here's how this starts. We also learned that every accumulation function expressed in open form as go. Okay, what kind of accumulation functions expressed in open form did we learn about? Who can tell me what kind of expression, what kind of open form accumulation functions did we learn something about? Yes?
The integral from a to x of the rate function.
The integral from a to x of the rate function. Agree with that? You should. You should, okay? Every accumulation function expressed like this as the integral from a to x of our rate function with respect to t dt can be expressed in closed form as what? Go. One more line to this. One more line. So the thing we've learned is that we can express capital F of x in closed form. How? How can we express capital F in closed form? Yeah. Which one? No, but we're not going to express f of x in terms of f of x, right? So, let's try again. Right. Z of x minus z of a, right? Because this is expressing the accumulation of a quantity, right, bit by bit, as x changes from a to x according to this rate, right? But now we know that we have this rate's accumulation function, so it's the same as the total accumulation up to x, right? Final value of accumulation minus the total accumulation up to a, the initial accumulation, right? So we can express capital F of x as z of x minus z of a. Okay, this is the fundamental theorem of calculus. It's two ways of looking at the same accumulated quantity. It's two ways of looking at the same accumulated quantity. As accumulating bit by bit, starting at a and ending at x according to that rate, or looking at final value of accumulation minus the initial value of accumulation. Right? So this is everything accumulated up to x minus everything accumulated up to a. And so that final value minus initial value will give you that same total amount of accumulation that we do bit by bit here according to that rate. This is a really important principle. It's the fundamental theorem of calculus. Okay? And so before exam 2, we were finding exact accumulation functions, but this was as far as we could go. Once we could express it this way, and then we needed a GC, our computer, to give us values of accumulation, values of capital F. Right? This is called an open form representation of a function because it doesn't spit out values of the dependent variable nicely, right, for us, just with easy calculations. But this does, right? This, plug in x equals 2, it gives you that amount of accumulation. Plug in x equals 10, gives you that amount of accumulation easily, right? Because it's just elementary operations and functions. Okay, so now that we're finding these rate functions in closed form, it always gives us another thing. We can go back and say, oh, for that accumulation function with that rate, we can write the accumulation function represented in closed form now. So we've revisited this several times. We've read about it in the text. Is it starting to make sense? This is for some, hopefully. But it needs to make sense for all soon, okay? All right. So let's talk about another function, the square root function, okay? I want you to write the first step in deriving a closed form rate of change function for this function, square root of x. Go, everyone should be able to do it. What would the first step be in deriving the closed form representation for square root of x? Okay, tell me. First step, someone in the back row. Anyone got it? Don't be shy. I know Joseph's got it. Yes, sir.
We represent the square root of x as x to the 1/2.
No, we want to. Yeah, we're going to do that eventually, but that's not what we're going to do now. We want to think about the first step in deriving any rate of change function. Any rate of change function. What would that first step be? Yes, sir.
We look at what type of rate of change or how to change that into a rate of change function, like
Okay.
how we did it on the last one.
And how we've been doing on all of them. So what would it be for this one?
Rate of change is the square root of x.
Which is, how would we start to derive that? What would the first step be? And tell me what that is for this. That's right. Square root of x plus h minus square root of x all over h. You should have gotten that. Because this is what? F of x plus h minus f of x over h. Every time we derive a new rule, it's always going to go back to our rate of change function. F of x plus h minus f of x over h. That's really important. We've been doing that every single time now. So we need to what? We need to get h out of the numerator, right? Somehow we got to get an h out of the numerator, so h over h goes away and becomes 1, so we can figure out what this will be like when h is essentially 0. Okay, so from algebra 2, you got this rule. A minus b times a plus b is a squared minus b squared. And this will be nice because if we could get this squared minus this squared, those would take the square roots away, right? So what would we, using this rule now, so what would we do to this to get this squared minus this squared? What are we gonna do so that in the end that numerator could be just x plus h minus x, or the first thing squared minus the second thing squared? So we're gonna look at the left side, right? We've got a minus b, so we're gonna multiply by a plus b. A plus b. But if we do that to the numerator, we have to do that to the denominator. So we're going to multiply the top and bottom by a plus b. See it? And now we know that numerator is going to simplify really nicely. Is it okay? So now applying the rule, we're just going to get a squared minus b squared in the top, which is x plus h minus x. And the denominator, we don't just hold on to it like it is. We don't have to do anything with that. So what does the numerator become? Just h, right? Just h. And there's our h over h. So we can say, see you later. And that's what we needed. We need to get that single h out of the denominator. And then we're going to let h get what? Really small to get the exact rate of change function. And we'll essentially have this. 1 over square root of x plus square root of x over, or 1 over 2 square root of x. Questions on that? So all you really need to know for this is just this kind of trick. This is called the conjugate. So radical x plus h minus radical x. Its conjugate is radical x plus h plus radical x. And we use that algebra 2 formula to make those square roots go away in the numerator. Questions on that? Okay, yes, please.
Aren't you supposed to not have a square root at the bottom? You're supposed to move it up.
Yeah, it's okay. It doesn't change the value of it. That's kind of a formality. You know, like that's kind of formality. But it does. You can still calculate things like this all day long. Divide by something and take the square root of it. So we're not going to worry about that formality. Other questions? What happened? I didn't even touch anything. That was bizarre. Let's try this other way here. Oh. I have no idea. I touched something over there. Okay. All right. Here we go. So, So we got another one, right? So we got another rule, and then someone suggested, notice that radical x is just x to the 1/2, right? And we already got a rule for something like that, right? We can use the power rule. So what will the power rule be on x to the 1/2? 1/2 x to the negative 1/2. Are they the same? X to the minus 1/2 means x to the 1/2 in the denominator, and that's what square root is. Check. Check, right? Okay, so our algebra is always prone to mistakes, so we're going to be doing these algebraic derivations. How can we check our result graphically with GC? How can we can graph this and then graph something that we can trust and see if they're the same. Okay, let's take a look at that. How can we do that? So let's GC here. Okay, so what was our function? Our function was square root of x. So let's say maybe algebraic derivation. We found that the rate function was 1 divided by 2 square root of x. So we want to check that. We want to make sure that that's actually the rate of change of square root of x. So you can do this for any function. I'm just giving you an example on this particular one. So now, what about what is our trusted form of the rate of change? What do we know for sure that would give us, we know for sure would give us the right rate of change function? What do we know that would do that? Because this was the result of a bunch of algebra we did. And just because I had it in a nice PowerPoint doesn't mean the algebra was all right. So what's our trusted form?
Trusted form, you use the power rule.
No, but the power rule is based on the algebra too. So what is our absolutely trusted form for rate of change? What's that?
Fx plus h.
Right.
Fx.
Yeah. So our trusted form would be, say, let's call this T, capital T. Use capital R. Capital R. Capital R equals what? Okay, if I've got f of x equals radical x, then we know for sure that the rate of change is f of x plus h minus f of x all over. Now we have no, as long as I've typed that in right, there's no qualms about that. We know that that is right, okay? If what? To get the exact rate of change? H equals 1? 0.5? Small. How about that? Okay? It's nice and small. Okay, so we want to then graph them both. So y equals r of x, and y equals capital R of x. And let's just graph, we'll turn that one off. So we'll graph the one we found first. This is what we found algebraically. And when I turn on the next one, when I turn on the trusted form, f of x plus h minus f of x over h for a very small h, if our first one is correct, then what should happen? Yeah, they should just land. So I'll do it in red, and hopefully we'll get black. Yep. Or indigo. Red plus blue. Okay? All right, so trusted, or the one we found, turn on the trusted form. It's exactly the same. I can turn off the one we found. Okay, so this will be an important tool for you for checking rate of change functions that were dependent on you doing some algebra. Okay? This is always right as the rate of change for a small h. Okay, cool. Any questions? Nice. Okay, so let's do some more here. Where were we? Oh, crying out loud. Okay, here's another one. We want to find, so this is b to the x. Notice this is not x to a number, b to the x. Totally different kind of function. This is an exponential function, right? It's some value, some fixed value raised to the x power. That's not a monomial, x to the something. Totally different kind of function. So it's going to have a totally different rate of change. It is not xb to the x minus 1. Although thousands of calculus students throughout the ages have tried to write the rate of change function as x times b to the x minus 1. This is a totally different kind of function than x to the something. So it's going to have a different approach to its rate of change. So write the first step for deriving the rate of change for b to the x. Write the first step. Go. Okay, how did it go over here? Did you get it? Yeah, you. Did you get it? Log? Don't assume you know anything when you come into this class before. I want to know how do we start deriving the rate of change function if the function is b to the x? Do you want to try again? Okay, go ahead. Right? She got it. That's it. So the rate of change of f, in this case, is going to be b to the f of x plus h minus f of x all over h. Okay, so what do we do with this? We've got to do something with the numerator here. Again, we want to simplify something in the numerator. So we have to know our laws of exponents. How can we rewrite b to the x plus h? Anyone know? It's actually b to the x. So x b's multiplied together, and then h more b's multiplied together, right? Isn't that the same thing as that? What do exponents mean? It's the number of times you're going to multiply that number together by itself. So if you're multiplying b together x plus h times, then you can just group x of them and then b more of them, h more of them, right? So x number of b's and then h more number of b's, and that's what that says, okay? And what can we do with that? Factor out b to the x. Now, we're not getting that nice h popping out in the numerator that we can simplify with the denominator. We got this instead, and we can't go much further. So this takes a different approach, okay? This takes a different approach. We look at this right here as a whole, and we say, when h gets really small, essentially 0, that thing does what? So what about b to the something very close to 0 is? 1 minus 1, 0 on the top, 0 on the bottom. So what we have is called 0 over 0. This is an indeterminate form. If you remember that, meaning in different situations, when ratio is essentially 0 over 0, or getting very close to 0 over 0, in different situations, that could mean different things. Case 1. Uh, 0. Case 2. Really, really big. Or case 3. A constant. So let's see what makes sense in this case. So if that ratio went to 0, what would our rate of change function do? It would essentially be what? If we had case 1 for 0 over 0, then what would the rate of change of f be? 0. Is that going to be right for an exponential function? No, an exponential function is not constant, right? Constant functions have a rate of change of 0, but not exponential functions. Case 1, not true. Okay? Next case. If that ratio gets very, very, very large, as h gets close to 0, then what we're saying is that then that whole thing will get extremely large, and then the rate of change at any value x would virtually be infinity for an exponential function. Does that make sense? At any value of x, the rate of change is infinite. No, that doesn't make sense. That doesn't make sense. Okay? Exponential functions look like this. Is the rate of change, are these rate of change so big that we couldn't find them? No, we could zoom in and we could take our change in y and change to x, and we could get lots of different rates of change for that. Case 2, not the case. Therefore, in this particular reasoning about exponential functions, we must have case 3, that this thing, as h gets really, really small, becomes a constant. So essentially what we have is, for small h, b to the x times k, some constant. So notice, what do you notice here? What's b to the x? Look familiar? It's our original function in the first place. So the rate of change of an exponential function is just a constant multiple of the original function. Right? It's just a constant multiple of the original, whatever the y value is, at any value x, your rate of change is going to be a constant multiple of that y value. Okay? Now this turns out to be, this constant, without figuring it out, turns out to be natural log of b. And that's what she was talking about. So this then becomes... So our rate of change of b to the x is b to the x times k. And that k turns out to be, we're not going to prove it, we're not going to show it, but it turns out to be natural log of b. Okay, so let's just investigate a couple of these here. So look at, what if, say if I had, say g of x was 2 to the x, and say h of x, or j, let's do j of x is 3 to the x. Okay, so I want you to find the rate of change of g with respect to x, the rate of change of j with respect to x. Just apply the rule now. Just apply the rule. Okay, rate of change of g with respect to x is 2 to the x times natural log of 2. And then I want you to find the natural log of 2. And then 3 to the x will be 3 to the x times the natural log of 3. Find that. So find natural log of 2. 0.693 ... Okay, natural log of 3. 1.098. So when it's 2 to the x, your rate of change is a fraction of the value of the original function. And when it's 3 to the x, the rate of change is a greater value, right? So it's a multiple greater than. So what question does that kind of begs a question here. There's a really special function that we're kind of honing in here on. So I'll call it, I don't know, q to the qx. So for some value, this natural log of q, natural log of that base, let's call it capital B. Question mark looks weird. We'd really like to know for what b, that natural log of b equals what? 1, right? Because if it equals 1, then what happens? The rate of change is the same as the accumulation function. There's only one function in the whole universe like that, where the value of the function, the accumulation at any given point, then is same as the value of how fast it's changing at that point. There's only one thing like that. So for what value of b is the natural log of b 1? Yeah. E, right. There's this number e, okay? E is, I'm going to write it out, 2.7182818245945. Okay? So this number is the value of b for which, when we get that constant ln of e, is 1. And so we have this very incredibly special function where the value of the dependent variable is the same as how fast that variable is changing at that value of x. The rate of change function is the same as the accumulation function. It's the only function of its kind. Okay? Oh, so before we do that, let's look at that on GC. So here's y equals e to the x, okay? Okay, what's your favorite value of x between 0 and 2? What is it? Not interesting enough. I heard 1.7. So let's go here to 1.7. There's 1.7. I've got the point 1.7 comma 5.47395. Okay, what can you tell me about, what else can you tell me now about this function at 1.7? At x equals 1.7? Yeah. Yeah, not only is the value of y, or the amount of accumulation, 5.47395, but this function is changing at a rate of 5.47395 at this moment, 1.7. Let's prove it. How can we prove it? How can we show that? What should we do? How do we find the rate of change? Zoom in until we see what? Essentially a linear graph. So now we've got a moment here. So here's we'll go from 1.69 to 1.71. Ready? Write it down. 5.419. Jot it down. Okay, that's at 1.61 and 1.69, sorry. 1.71 off the screen, but we still get the number. 5.52896. Go. 5.52896. What are we going to do? Somebody new. Somebody new. How about in the back row? How about in the pink shirt? What am I going to do? What should we do? Where were we going with this? Yeah. Tell me. Yeah. I'm going to switch it if that's okay. How much? What was my change? 0.02? 0.02, right? And what do we get? 5.474. So the rate of change at that moment was the same as the amount of accumulation at that moment. And so, and we could have, that would be the same, be true for every value of x, not just 1.7. Any value of x that we pick, its value of accumulation will be the same as the value of the rate of change. Pretty cool. Okay, so what is the meaning of this? And what else could you, so what is the meaning of g of x equals integral from 4.5, 10 to the t, ln of 10 dt? And what else can you say about it? Discuss. Discuss. Okay, somebody new who can articulate the meaning of that function g of x, capital G of x. What do you think? How about anybody? What's the meaning of it? Okay, Joseph, go for it. Okay, is there any more to it? If? What? So, of any functions, the amount of accumulation of any function from 4.5 to x? So, it's precisely what accumulation is it? Yeah.
You can find out the function of g of x.
No, we're talking about the meaning. That's next. Talk about the meaning. What's the meaning of this? It's the amount of accumulation from 4.5 to x if, or according to, oh guys, rate of change. Rate of change is 10 to t ln of 10. If you don't have a rate of change function, there's no way you can know how much accumulation you have. Okay? So according to a rate of change of 10 to the t ln of 10. Okay, now you want to talk about how else you could write g of x.
You can write it as 10 to the power of
10 to the power of x. Agree? Mm-mm. Oh, someone please no. Yeah. So g of x is 10 to the x, what? minus 10 to the 4.5. What accumulation function has this as its rate? Ten to the x. 10 to the x. The rate of change would be 10 to the x ln of 10. So this is the rate of change. Then that accumulation function is 10 to the x. And so then this accumulation function could be written as final value of accumulation minus initial value of accumulation. 10 to the x minus 10 to the 4.5. Okay, we got to keep practicing that, evidently. What is the rate of change of b to the x?
It would be the b to the x times the
Now,
log of b.
so now, I give you a rate function, 10 to the x, ln of 10. What do you know?
Yeah, that's the words get too close.
We know that it is b to the x here.
The accumulation function is what?
B to the x,
We know what b is.
which is
10 to the x. 10 to the x. Our accumulation function is 10 to the x. And the rate of that is 10 to the x ln of 10. So here I'm giving you an accumulation function at a rate of 10 to the x ln of 10.
You also say that out of nowhere, starting from 5 to x, that t power not
ten.
But this is the accumulation, right? It's the integral. So integral is summing up a bunch of little bits of accumulation. Rate times change in x, rate times change in x. We're summing up little bits of accumulation. This is nothing new, right? But now, here's, if this is the rate function, when we derive this, we know what the accumulation function is for this rate function. It's 10 to the x.
Yeah. And then we're just doing it from 4.5 to x.
So this is the same thing we're saying, that if you when we found that rate of change function, we also know how to write this accumulation function represented in closed form.
Okay.
The final value of accumulation minus the initial value of accumulation. We did it at the beginning of class with the z function,
That I
remember?
understood.
It's the same thing. This is the same thing.
The natural log was thrown in, and how we're going from accumulation to rate and then back to accumulation.
We did the same thing at the beginning of class in the z example. We started with the z, we found the rate of change, and then we said, look, we can write, now given an accumulation function at that rate that we just found, we can rewrite it as the difference of amounts of accumulation using the z function. It's the same thing. It's exactly the same thing.
Okay. I see that now, thank you.
Does that make sense?
That does. That really does.
So Mark, I told Cerny about what to do